Hey, how's it going? Today is day 2 relearning calculus because I'm unemployed and I've got too much free time on my hands. I'm an ex-Googler and I love mathematics. I used to study pure math way back in the day, and now I'm trying to rebuild math as a hobby. Yesterday we worked this problem, so I wanted to repeat it at the beginning of the video instead of buried in the middle of a 3-hour long live stream. So I think that could be a good way to try to make the opening a little bit snappier, and because I can see 90% of you all click away within the first 30 seconds. And that makes sense. I understand. So it's just the nature of a live stream, if you ask me. So here, you may be reading it already. We are working on functions and just defining what the hell a function is. And here's the first problem. So true or false and why. Functions are the same as equations. The domain of every function is a subset of the real numbers. F of x equals 1 is a one-to-one function. Every global maxima is also a local maxima. Every local minimum of a function is also a global minimum. The graph of a function can never cross one of its asymptotes. Average rates of change can be thought of as slopes. And finally, a function can have different average rates of change on different intervals. So go ahead and pause the video right now if you want to work this problem on your own. 3, 2, 1. All right, let's keep going. So here's my solutions for all of these that we did yesterday and I just rewrote. Functions are the same as equations. False, for example, the equation of a circle is neither a function of x or of y. The domain of every function is a subset of the real numbers. This is a great example. So I created a function yesterday that has nothing to do with numbers. A function is always just a rule. You give it a thing and then it gives you another thing. It does something or it returns another value. So I created yesterday the function of reactions, which I'm denoting by fancy R right there. This is the function of reactions to the math hobbyist videos. Okay, so if it's the first video that you've seen, you're going to like and subscribe. And then otherwise, if it's another video that you've seen, it's not the first one you've seen, you're going to like it. Okay, so this is the function of YouTube reactions specifically to the subset of the math hobbyist. Now, there are interesting properties, like for example, Mr. Beast videos is also a subset of all YouTube videos, and the math hobbyist videos is also a subset of YouTube videos. You'll see that reactions to both of those are very different, and it also depends on the person, but generally speaking, there exists videos in Mr. Beast such that your reaction to that is going to be to dislike it, right? But there are no math hobbyist videos. There are no math hobbyist videos such that you dislike it, right? That's a silly example for real. But I think it's very important to try to come up with an example of something that doesn't have anything to do with numbers. It's an abstract idea of a function. And I called this like and subscribe, dislike, and I guess technically dislike and subscribe, and then do nothing. Click away. For math hobbyist videos, it's like this. Everything goes to like or like and subscribe. And for Mr. Beast, you get the picture. And so I use this also as an example. This function is neither onto nor is it one-to-one, because there are multiple videos that you're going to like. and there are no videos that you will dislike. So, this, maybe we call this one function 1, function 1 that goes from the math hobbyist videos, from that subset of all videos to reactions, is neither one-to-one nor onto. So we define those terms and we will continue. Okay, so all right, that's a dumb example, but I hope it sticks in your head. You know, like coming up with dumb examples is the way to get things to stick in your head, if you ask me. All right, next question. F of x equals 1 is 1-to-1. That's false, because there are two x values that both map to the same y value. So just like in this silly example that I came up with, there are multiple videos that you're going to like. So therefore, this function is not 1-to-1. 1-to-1 means every output has exactly one input. And here, there are two inputs, 0 and 1, that both equal the same output of that function. Every global maxima is also a local maxima. Yes, Taalman defines this in terms of near. For all x values near a point, that the local maxima is the greatest value. We can make that a little bit more precise by talking about an interval around a point, like all the x values less or within one less or one bigger, for example. Anyways, I'm not going to get into the formalism on that one. Doesn't matter. Every local minima of a function is also a global minima. So that's false. We need to provide a counterexample. And this function is a good counterexample. I drew it first, and then I tried to remember, how the heck do I write that down? Oh yeah, it has 3 zeros. Like maybe I want a 0 at -1, at 0, and at +1. So that second term corresponds to the 0 at -1. Like if you plug in -1 into that term, it's 0. If you plug in +1 into this third term, then that one is 0. Or clearly, if you plug in 0 into x, then that x is 0. Now, the graph of a function can never cross one of its asymptotes. That's false, and Taalman gives this nice example in the section. So this function crosses one of its horizontal asymptotes. Now, is it true for vertical asymptotes? I don't know. I mean, it just really depends on what you mean by can never cross, because what about, wait, no, it's not that. What about the function 1 over x? Right? Oh, wait, even 1 over x. 1 over x has a horizontal asymptote. Oh, and never mind. It never crosses the horizontal asymptote. It never crosses that vertical asymptote, but what if you define it to be 0? Like, f is 0 if x is 0, otherwise it's 1 over x. Did this function cross that vertical asymptote? I don't know. That's kind of like it depends on your definition. Like, what do you mean? What do you mean, lady? What do you mean by cross? All right, let's keep going. Average rates of change can be thought of as slopes. Yes, that's true. We defined, or briefly defined, the average rate of change is the change in the y value divided by the change in the x value. So you take 2 points, A and B, and then you find the change in the value divided by the change in the input. We also often call that rise over run, at least in America. That's the saying that we say. It's rise over run, and then that's the slope of a line. Yeah, and then like the section actually clearly states that it's thought of as slopes. So a function can have different average rates of change on different intervals. Yes, that's true. The function x squared is a nice example. From 0 to 1, you've got a line. If you take the point 0 and the point 1, 1, and therefore the average rate of change is going to be 1. But if you take the points at -1 and +1, then you have a horizontal line, and the slope of that is 0. So there's our solution, and it was very good for me to practice just rewriting it and making it a little bit cleaner than yesterday. So I think I already crossed it off, but just making sure. Yep, we crossed off number 1, and I just wanted to show I have taken some time. Taalman has a lot of exercises, y'all. Like, it's a beautiful book. This is a beautiful book. I'm smitten. I'm like awestruck by this book. It's actually gorgeous. It is a Calculus 1 book, but it's written in the style of a pure math book, but also written like clearly organized to be useful for engineers too. Like it really tries to just make everybody happy, and you can make everybody happy if you get rid of the cartoons in the margins. So go get this book. I will set up an affiliate link at some point. I don't know how to set up affiliate links, but I'll figure that out if there's demand. But it will, the URL by tonight will be TAALMAN the math hobbyist.com. This one will be an Amazon link specifically for this calculus book. I'll also set up like calcbook dot blah 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 and books dot blah 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 books dot blah 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 themathhobbyist.com. And yeah, I'll try to keep those up to date. These are the books I recommend that I love, that we're working through, and you can work through them with me. Cool. So I wrote out some of the sections. Here's my prep for today. I wrote out a bunch of the sections, and so we can see an idea of where we're going to go from here. So section 1 is functions and graphs. And I wrote out explicitly every single number. And then I realized, wait a minute, what am I doing? I'm no longer working in pen in one of my tiny Moleskine notebooks. I don't know where one of them went. I have like a lot of these. This is my favorite way to do math. Pen, black pen. I'll also set up an affiliate link for these pens, but you know them, the Pilot G2 or whatever pens in a Moleskine notebook. And on the last page, starting on the last page, I write out a table of contents in pen, just like this. And I know it's going to take a while, but I want to cross off every single one of those. I'm just going to rip through this to-do list over time. But then I was like, wait a minute, we're using a fancy digital pen now in this amazing app named Notability. Go get it. It's great. So I'm going to take a shortcut. So here's our new notation. A dot 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 I is all the prefix problems, A through I. And then we have 0, 1, dot dot dot, 21, dot dot dot, 81, dot dot dot, 85, 95, 98. The reason that I didn't just do 0 dot 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 98 is that Taalman has this incredible organization. And I want to take a moment again to just say how neat it is. There's always a problem 0, and it says, write your own damn notes. Take notes on the section. It literally just says, take notes. Create your own summary of the section. And it's the same problem in every single section. It's always create a summary of the section, which is just so funny to me that she takes the space in every problem set to remind you, create your own summary. Do it. I mean it. I've said it 20 times by now. But I still mean it. So we do notes. I'm pretty sure next is concepts. Oops. Here, why don't we get a little more colorful, because color is nice. So first she always says, take some damn notes, and then there's a bunch of problems that are concepts. And then there are a bunch of problems, pretty sure, are skills. And then, what comes next? Applications, I think. And then we organize with proofs. And then, finally, we wrap up with, what's the next color? Yellow. Finally, we wrap up with thinking forward. Also, I forgot to label this one. This one is I forget what she calls it, but it's review. It's looking back. So every section always has review of fundamental concepts, then take notes, then concepts, then skills, then applications, then proofs, then thinking forward. It's so organized. It's really cool. I've never seen such an organized undergraduate. Undergraduate's the wrong word. General purpose math book, something like that. I don't know. It's really nice. So, any questions? Leave a comment down in the comment section below. But otherwise, let's just get going. So we've already done one from the first section. I want to take a look to this point and see what's the difference between concepts, and let's do our first skills problem from section 0.1. And we're just going to bounce around. We're going to be all over the place in this stream. So I'm going to jump a bunch of sections or just change books. We're going to be all over the place. So now we're going to do number 27. I still feel confident that that's not going to be that hard. And then can we do an application? 79. I feel confident in my math skills. I'm going to say that that might be easy. But even for me, I'm going to say that any proofs are never easy. like, hold me to that, y'all. If I'm being an asshole and I'm just like, oh yeah, this proof is easy, this proof is trivial, call me out on that, because they are never easy. 96 and then 97. Thinking forward, I have no idea what to expect in the thinking forward section, but this is 97. I'm going to guess that it's not going to be the hardest thing ever. Hey Ben, how's it going, man? Thanks for swinging by. I need to respond to your email, but I guess I could respond to some of it right now. Yeah, Markov chain sounds like a lot of fun, dude. I'm really excited to try to learn more. In my prior video, which, like, all these videos are like hours long, so I never would expect you to like actually go back through hours of video, but just a teaser. I'll create chapter markers and things like that at some point. I think I've already created this URL, slime.themathhobbyist.com. It is a amazing PDF, a brilliant PDF on how it's impossible to get anything done at large tech companies and any large company like Google. It was written by a Googler before they left, and then here's like a public version of this PDF. But like, we all love to share it with each other internally. The internal version had more math. But yeah, like, you can... I think that the internal version explicitly called them Markov chains. And you calculate, like, even if everybody is well-intentioned and everybody has a 99% chance of doing the right thing on the project, even if you assume that, as the number of employees goes up, this tends to a project failing. I mean, that's just like the very beginning, but there, like, it really dissects all of the various factors that can lead to projects failing, including like interpersonal conflicts and like a lack of loyalty between different teams, and everybody rightfully having 10 different things that they could be working on, and not everybody's in alignment on what the most important thing is and other stuff. So, all this is to say, I would love to learn Markov chains and Markov systems myself. And this might be our fun, motivating example that I try to like build up and up as an example of a Markov process. Like, how it's impossible to get anything done at Google. All right. Anyway, so that's what I was trying to point at with that video. Today, this week, we're doing calculus. And right now I'm just admiring how organized and beautiful this book is. It's not a paper, it's a slide deck, but it's fantastic. It's got a lot of emojis, but there's like very serious, really good stuff in it. You haven't experienced industry yet. You're still in the ivory tower, the beautiful ivory tower where everything is nice, but in industry, things are very messy. Anyways, this is the book that we're starting for calculus, and it's gorgeous. It is freshman calculus, but it's written in the style of like a Bourbaki, I guess Bourbaki, but like it's written in that logical style, and it's like so clear, so organized, and there's no cartoons in the margins. Like, it's just straight up math. But also including applications, also written for engineers, and it has, every section is so organized, like every section of exercises is so organized like this, like review, notes, concept, skills, applications, proofs, and thinking forward. I wrote out the sections of the table of contents. Like, this crazy lady even gets into delta epsilon proofs in freshman calc book. Like, in a freshman calc book, she actually does like a formal definition of a limit and delta epsilon algebraic definition of delta of limits, which is super cool. And then the other books that I'm considering in the calculus series are going to be applications, like a book on applications, which I'm going to call differential equations. I bet that there's a lot of good applications to the real world in this book, like the heat equation or whatever. I'm also stretching a little bit. Well, sorry for this side, everybody. I know that you all are... The people watching the videos after the fact have already dropped off by now. But we get the same pattern. This book is much smaller than the other book I was holding a second ago. It's much smaller, maybe about the same number of pages, but like the area of each page is much smaller. And then that's a medium level book. This is a hard book. I had it labeled as medium yesterday, but no, I was reading it again. This is a hard book. This is just a straight up hard book. And so probably tomorrow I'm going to write down the definition of a limit according to Taalman, according to Rosenlicht, and then according to Spivak. So this book is much scarier than this book, and they just keep getting smaller. Like the tiny books are the scary ones, right? And this one's this one's the same size as this book, so I really think that they're going to be just as hard as each other. This topology book, I'm going to write down the definition of a continuous function from this book as well. So we're mixing and matching and doing a really random ADHD math stream over here. Let me answer. Okay, so yeah, Markov chains have wonderful structure, a lot of linear algebra too. Yeah, it's a perfect context to teach linear algebra, I think. When I TA'd for a linear algebra course for 2 semesters, the professor would use Markov chains as one of the motivating examples of matrix multiplication, and showed how like they can be used to build like a really simple iPhone autocorrect, like the keyboard predictions, and you just keep hitting the first suggestion every time, and you get these like ridiculous sentences. Yeah. Hey, Keanu, dude, thank you for the sub. Appreciate it, man. Let me know what you like, what you don't like about this. I'm very much open to feedback. What do you like? Why did you sub? I appreciate it, man. I love that. Calculus is sometimes made a bit patronizing in some books. That's perfect. Like, this book is not patronizing at all. Like, Taalman is not patronizing. And that's something I want to do in this stream. Like, I want to avoid any of the math that I'm showing here. I don't want any of it to be patronizing, even to a wide audience. Like, I'm going to do some quote-unquote easier concepts, but then I'm going to be like, the same concept I struggled with in upper division classes. Like, it just gets harder and harder and harder, and I got super stuck and couldn't figure out this shit, so, you know, I had a hard time at some point. And so it's okay. Everybody gets stuck. Like, don't worry. Like, professional mathematicians get stuck. Like, 99% of the time, mathematicians are stuck and don't know how to solve a problem. 99.9% of the time. But if you go into it as a career, it's because you just love that 0.1% so much. That moment of solving a problem and that eureka moment, it's like a drug. You're just chasing that all the time. You're like, I want that moment of enlightenment that solving a hard problem gives you. That's what I always like to tell kids who are struggling. I don't use the word drug, obviously, but anyways, this is a math stream. How's it going? So I wrote out table of contents for some of the other books we're going to be mixing and matching with. Rosenlicht. I had to double check, and yeah, Rosenlicht just defines everything in metric spaces. So I'm going to soon be, probably tomorrow, write down the definition of a limit in the real numbers according to Taalman, and then in an arbitrary metric space according to Rosenlicht, and then Papa Spivak. It's on like page 5 or something. Continuity according to Big Boy Spivak. And then at some point also the topology definition of continuity. Is there a limit in topology? Quite literally, we have a topologist right now in the chat, so you would be able to tell me. I don't think so, right? Like, kind of by definition, a limit requires a neighborhood around a point and some concept of like distance. So that's fair to say, right? There's continuity. There's certainly continuity in an arbitrary topological space, but I don't think that you have a limit, do you? Remind me. Like, is that the difference? Like, a metric space has... You can define limits on metric spaces, but you can't define limits on topological spaces? All right, Keanu. Well, it's my first year in PhD program. Heck yeah, I want more PhD people in the chat, as well as, like, we have, like, some math hobbyists and undergrads, like, first-year undergrads and things. But it would be great if we have just a blend, you know, like some algebraic geometry. That's badass. Cool. So you're studying algebraic geometry soon, and by soon I mean within the next few years. At some point, we'll be getting, once I dust off all the cobwebs in my rusty head, I'm going to be cracking open Lang algebra, and we're going to be we're going to start on Eisenbud. Commutative algebra with a view toward algebraic geometry. Someday we're going to tackle these books. I see. Yes, there is, but without distance, but with smaller neighborhoods instead of distances. Cool. I've forgotten everything, so I'm looking forward to relearning that. Oh boy, the big guns. Yeah, we'll get there someday. And these will be the red books. I'm retiring the joke, but it's maybe the last time I say it. But I have 2 different shades of red on this iPad. I've got this nice life-giving blood color. You know, this red that I've been using is like a nice life-giving blood. And then you may see where we're going with this. That's in contrast to this dried blood. Papa Spivak is the color of dried blood. That is the book that kills your dreams. That book kills. You're dead. That book killed you. You're dead. You're not going to grad school. You decided not to. All right. That's officially the last time I'm telling that joke because it's too morbid. Let's move on. I did Taalman 0.1.1 yesterday. Gotta pop off, but I'll see you later. Bye, everyone. Yeah, good to see you, Ben. Thanks for stopping by. Okay, so yesterday we did Taalman 0.1.1, and the only thing I want to point at to Keanu, who's new, we have a bunch of true or false questions. The domain of every function is a subset of the real numbers. I like this example I came up with. Imagine the function, going from the set of math hobbyist videos to reactions. This is a function that is not defined on real numbers at all. The domain is YouTube videos, and the codomain is the set of reactions. The range of this is the subset like and subscribe and like, whereas the codomain is this bigger set. Do nothing, like click away and do nothing, like and subscribe, like, dislike, or dislike and subscribe. Those are the 5 possible reactions. And the function from the math hobbyist videos to reactions is defined as like and subscribe if it's the first video you've seen, and like if it's otherwise. But for every math hobbyist video, those are the only possible options. Just joking. Okay, so thank you. I'm going to... People cry from reading Eisenbud? Okay. Yeah, I think I was just... I was wanting the scary stuff when I got that book. I will look into that one. That sounds great. I do want a gentler introduction. Chamber Lior. I will screenshot that and hopefully write it down somewhere. Thank you. I don't know why I can't screenshot that. I will remind myself. Commutative algebra. And I've been telling this joke that the books get smaller and they also the subjects sound easier. Commutative algebra somehow sounds easier than algebra, right? And algebra sounds easier than calculus. So I will look that up. Chamber Lior. Okay, thank you. Okay, so finally, what I'm trying to get to is writing down the next Taalman exercise, and let's solve some problems together, y'all. Hopefully, I'll get stuck. I'll start getting confused at some point. 0 point... I'm just going to do a couple from this chapter, just literally defining functions so that we have a wide audience. Taalman 0, 1, what do we have? 0, 1, 27. So this is a skills problem as opposed to concepts. And the reason that I want this is I want to get a better feeling for what is the difference between concepts, skills, applications, etc. All right, so 0, 1, 27 says, before all of these problems, find the domain and range of each function use a graphing utility. Use a graph. That's so boring. Graphing. Ask ChatGPT to draw you a plot utility or plot points. Okay, we could use our brain. It's up to us. We could ask ChatGPT or just plot points to sketch a graph of the function and illustrate the domain and range of each. Okay, so 27 says f of x equals square root of x minus 1. Okay, so the square root function looks something like that, I think. Wait, no, that's not right. That's not right, is it? I'm confused. Oh my god, okay. So, square root of 0 is 0. Square root of 1 is positive 1. Square root of 4 is positive 2. The square root of negative 1 does not exist. Yeah, so here we go. So this is y equals the square root of x. So if we replace every x with, if we replace that with x minus 1, then now x equals 1 is when y is 0. X equals 2 is when y is equal to 1. And x equals 4 is when y is equal to 2. So, this is a translation of 1 unit to the right. I'm explaining things because I do want these to sort of be to a wide audience. I don't know how well that's going to translate. I imagine that I could clip individual little problem solutions and post them. But I don't know. Yeah, so now the question asks to find the domain and range. I'm going to say that the domain of f is going to be the interval from 1 to infinity. The range of this function is going to be the set of values 0 to infinity. And it says illustrate them. So, I don't know. We could draw things in yellow for the domain. And we could draw things in maybe green for the range. I think that that's a decent answer. Okay, so we did 27. That was pretty easy. I feel good about it. Let's cross it off. That's kind of a boring problem. Let's do something a little bit. For me, it's a little boring, but I'm not saying it's easy. It's not easy. I want to make sure I don't. Let's just do a couple more. Why not? Now that we've stated, we know what these are. 28 says f of x equals root x minus 1. So the domain of f is all of the x values that we're allowed to plug into it in some sense. All the x values that it takes, which is going to be all x values greater than or equal to 0. And then the range of f is going to be -1 to positive infinity. And it's also going to look like this, but now we translated by adding -1 to every point from our original canonical graph of the square root function. This one has y equals square root of x minus 1. Like we shift everything down by 1 unit, like 1 comma 0 instead of 1 comma 1. Let's rip through a couple more of these. F of x equals 1 over x plus 2. F of x equals 1 over root 5 minus x. (31) is 1 over x squared plus 1. (1 over x squared minus 1). Okay, let's get all of these. So here, I don't know, domain of f and the range of f. And maybe we'll do something fancy. Why don't we duplicate that a few times? Oh wait, oops. I'm not going to be able to move them over. Haha, how cool. Alright, so now we've got the domain and range for each of these things. And we should probably use a different color. Alright, so the domain of 1 over x plus 2. So the only x value that is not allowed is -2, because -2 would make the denominator 0 in this function, which is not allowed. So this is all x besides -2. We can write it in interval notation like that, or we can say all x either of these notations are correct and good. The range of x, okay. It's been a while. Let's remind ourselves, what does y equals 1 over x look like? So it doesn't exist for 0. At 1, it is +1. At 2, it's 1/2, right? At 1/2, it is +2. So, yeah, as I thought, it's one of these. As x gets really, really big, like 1 over a googolplex, that's going to be very, very small. So, there's that, and then we can kind of clearly see that on the other side of this asymptote, it's the same values, but they're negative instead of positive. So, I believe that this is going to be every value except for 0. Yeah, this can be any value besides 0. And I think that you could just solve for that to see that any value can be... oh, wait. Oops. That is y equals 1 over x. But then if we want to translate that to 1 over x plus 2, then now the problematic x value is -2. If you plug a -2 into that, then you get infinity or negative infinity. Like really, you just get an asymptote where the function is not defined. So it's the same line, or it's the same curve, just translated over 2 units to the left. Okay, so the range of this one, well, it's still going to be the same. The range is still negative infinity to 0 and 0. So all values other than 0. The domain of f for this one, what does this function look like? One divided by the square root of x. How do we... We'll remember it as we go. Hey, thanks for the 3 likes, y'all. Appreciate it. Thank you, y'all. Let me know what kind of math you want to see. Do you want to see easy math, harder math, etc.? Ooh. How to prove that pi is transcendental. That's a great aside. That's a great question. I think it's really hard. I don't think it's easy. Transcendental. Prove that pi is transcendental. I'm pretty sure that this is not easy. And I don't have any tips for you on how to get it. I would literally just have to Google. But I bet that Wikipedia has a pointer for it. Yeah, I don't think it's easy. But great question. Thank you for asking that. You want to see mid-level to hard maths. Okay, that's great. Thank you for the feedback. I want stuff for everybody, and the earlier parts of these videos are easier, and then we get into harder. Sometimes I might mix them. I don't know. I'm all over the place. Whatever people want to pay me for. If anybody wants to pay, I'll work on that. But I think it's going to be a while until we get Patreon subscribers and things. So right now, I'm tutoring kids. I'm tutoring like high school students and kids. So I'm just trying to kind of brush up and work through like a lot of simpler math. But I promise you, we are doing hard stuff too. So here's my table of exercises. I'm mostly doing Taalman. Taalman is really nice as a calc book. But then I also have these harder calc books, which include like defining everything in metric spaces, or Papa Spivak. This book is hard, and these are tiny, tiny hard books. I've also got like some topology over here. So I'm going to be mixing and matching in hard math as well as easy math. I think I just heard a knock, so I have to be right back. Be right back. Okay, we're back. It was a neighbor, not our door. So, what math are you in, Sam? What kind of math? Are you a college student? Are you a math major? What do you do? Nice to meet you. Right now, I'm trying to make myself feel better, so I'm working on easier stuff. 1 over root x. Okay, well, square root of x. Square root of 1 is 1. Square root of 0 is 0. Square root of 4 is 2. So then this one would be 1/2. Yeah, okay, so it's this lovely function. Oh, wait. What the heck? One. Oh, I was doing 1 over root x on this one, wasn't I? 1 divided by x. Well, I think that they both are kind of the same shape, right? It's just that one moves a lot faster than the other, I think. Yeah, right? Okay, so 1 over square root of x. 1 over square. Yeah, so this would include like the point 4 comma 1/2, 1 comma 1, and then 1 divided by 0 is not allowed. At x equals 1/4, x equals 1/4, this thing would be 2. Right? Because 1 over square root of 1/4 equals 1 divided by 1/2, and that is 2. Okay, so it looks very similar. It's like a nice, smooth, decaying function. It's just that one, kind of like the bend is like a lot steeper than this other one, I think. Yeah. So then if that's 1 over root x, then square root of 5 minus x, we should, and this is all not theoretical. I do have a couple of people who are watching and following along with these who are reviewing math and relearning math. And so it's not theoretical that I'm trying to show this stuff to it's not theoretical to be doing like the simple math at the moment. All right, so 1 over root x has, the domain is only the positive numbers, because we don't want to take the square root of a negative number, because then that's a different class. That's called complex variables or complex calculus or something. So we can think of this first thing as a translation. When you replace x with negative x, then every point on your original graph gets inverted over this mirror at the x equals 0 line. So that's a translation or a transformation from the original graph to this new graph. And then finally we have 5 root 5 minus x. So I always think it's easiest to think of specific points, like does this move to the left or to the right? When x is 0, then this is square root of 5. When x is positive 5, then we have the square root of 0. 1, 2, 3, 4, 5. So the point where this graph blows up and becomes problematic is at x equals 5. And it's still pointing in the same direction because we still have a negative x, and it's going to be something along the lines of that. So there were the two different translations or transformations to get the right looking graph. So that helps. The domain of f, we're allowed to put in any value less than 5. F admits any x value less than 5. So the round brackets are strictly less than 5. The square brackets, which I guess I haven't written any yet, like if I wrote a square bracket at the end, that would include x equals 5. Okay, so that's the domain. The range is going to be all positive numbers. Everything greater than 0. The domain of this function is all real numbers. Because any number that you plug into x is going to be greater than or equal to 0. You'll never get a negative 1 out of x squared unless you plug in the imaginary number I. The range is going to be from positive 1 to infinity. I feel good about that. Oh, wait. Nope. What? Yes? I think. What is the range of this function? Yeah, like if we have 1 over at x equals like we get the points like 1 comma 1/2, right? If we put in x equals 1, if we put in x equals 0, we get the value 1. If we put in the value 2, then we get 1/5, right? 2 squared is 4. 4 plus 1 is 5. So this, I can see, is going to tend to 0. Like, ... If we put in 100, then we'd have 1 over 1, 2, 3, 4, like 10,001. So that's basically 0. But then what happens if we put in, say, 1/4, or wait, no, sorry. 1 over yeah. So I think that we've got 0 to 1. This is going to be every number between 0 and 1. If we put 1/2 into x, then we would have 1 divided by 1/4 plus 1. 1 over 1/4 plus 1 is the same as 1 over 5 over 4, which is 4/5. So that's still less than 1. Yeah. Okay. I'm a dummy. I wrote down the wrong thing. That's a cool function. 0 to 1. F of x equals 1 divided by x squared minus 1. We can... This allows every value other than x equals 1. Because at x equals 1, the denominator is 0. And then any other number is not going to be 0. When you... x is not positive 1 and x is not negative 1. Both of those values are bad. Negative infinity to negative 1, union negative 1 to positive 1, union 1 to infinity. I feel like I don't know which notation is nicer, but those are kind of like two different notations for the same thing. So I skipped the graphs. 1 over x squared plus 1, let's do 35. Or no, not 35, 31. One over x squared plus 1. When x is equal to 0, y is equal to positive 1. When x is positive or negative... Wait, x squared plus 1 or x squared minus 1? Oh, x squared minus 1 is the new problem that we're about to look at. Yeah. 1 over x squared plus 1 is defined for the entire domain, or the entire set of real numbers. When x is positive 1 or negative 1, then this is 1/2. When x gets big, y gets small. So I think it's going to look... something like this. Yeah, that's a neat function. That's a nice looking function. Look at that. Beautiful. Now, number 32, this one is confusing me a little bit more. 1 over x squared minus 1. This one is not going to be defined at positive or negative 1. We're going to have some kind of explosion happening at those 2 points. If x is 0, we have y is negative 1. Why don't we draw in a different color? If x is 0, y is negative 1. If x is negative or positive, yeah, I think we're going to get this. And it told us that we can ask ChatGPT, so I don't know if I need to prove it. But, oh wait, is that? That's wrong. No, is that right? For example, if we will have points like 1/2 and 1/1/4 squared is 1/4. 1/4 minus 1 is negative 3/4. So the point that I'm imagining is negative 4/3. Yeah. So at positive or negative 1/2, we're getting something smaller than negative 1. This function is going to look like a nice little curve going down to infinity. And then when x is greater than 1, I think we get this sort of behavior. Somebody fact check me on that. So these two look similar in like how they're written, but they behave pretty differently. So those are cool examples that Taalman chose, I think. And the range, I think, is going to be negative infinity to negative 1, and then 0 to infinity. So that's definitely a more complicated function. Negative infinity to negative 1, union 0 to infinity. Neat. Cool. Now I get to cross off a bunch of exercises. So we did exercises up to 32. Nice. That's going to make me feel very nice. We did several in a row. 28, 29, 30, 31, 32. Can anyone post the question, please? Oh, yeah. The question is here. Taalman, you can pause the video if you want. Find the domain and range of each function using a graphing utility or plot points, sketch a graph of the function, and illustrate the domain and range of each. And then we have a bunch of functions. F of x equals square root x minus 1. F of x equals square root x minus 1. We have these different functions, f of x, and then I found the domain and range of each. Yeah, no problem. Nice to meet you. RK9 Gaming 9, how's it going? How are you? Cool, so we just solved a skills question. Now I want to take a look at an applications question. Applications 79 from Taalman. Taalman. We're just talking about functions today at the moment. I don't know. I mean, it's a word problem, and word problems typically are a little harder, so maybe we'll give this a green-yellow. Somewhere in between easy and medium is what I'm expecting. Let me write it out. It says, sketch and label the graph of a function that describes the given situation. So this is like a modeling problem. Like, I'm going to be told a nice story, and then I'm going to write down a function that matches that story. All right, story 79. We have, this is going to be nice and meditative, just writing out some stuff. It's been a while since I've written anything on paper or an iPad. It's nice to. An island warthog. Okay, warthog population. Nice. An island warthog population. That's nice. An island warthog population initially grows quickly but as space and food becomes sparse on the island, the population growth slows down. Eventually, the population of the island levels off at 512 warthogs. Okay, so pause the video if you want to work this one yourself. We're going to create a model for this real-world situation of warthogs taking over an island. So an island warthog population initially grows quickly, but as space and food become sparse on the island, the population growth slows down. Eventually, the population of the island levels off at 512 warthogs. I don't know. Just depends on how complex of a model we want here. So I think I'm going to say that time is on the x-axis. Maybe this could be days. And the y-axis is the number of warthogs. Okay? And I'm going to say time t equals 0 is the day of first warthog. Okay? So before the first day, there were no warthogs on this island, and then some crazy person brought, I suppose we have to say, you know what, let's make this even more complicated. Somebody brought one warthog on a ship to the island, okay? Until some other day, when somebody else, some other crazy person brought another warthog. As long as the first warthog was alive, then then they can start mating, making sweet warthog love and creating more warthogs. Okay, so time t equals 0 is day of the first warthog. I don't know, we have some other point t0, ti, day, whatever. And then, yeah, they're going to start mating, and it says that eventually at some point the warthog population levels off at the number of warthogs equals 512. Okay, so so they start reproducing like crazy. It says that the population initially grows quickly, but as space and food become sparse on the island, the population growth slows down. I mean, there's just like a lot of ways that you could draw this function. I don't know. Here's one. Maybe they just grow linearly, and then they drop, and then they go up and down and up and down until it levels off at 512. And then magically it just stays forever at exactly 512. This would be a piecewise function where the value is 0 for all t less than 0. The value is 1 for t between day 0 and the day of the first warthog mate. It's 2 between, well, then it's not 2. Now we're going to say it's, 100 warthogs per day for between T1 and between T1 and T2, and then it's negative because there's too many warthogs all of a sudden on the island, and now the population is dropping. So maybe now it's negative 100 warthogs per day. And then maybe it's positive 50 warthogs per day, and then it's negative 50 warthogs per day, and then it's positive 25 warthogs per day, and then negative 25 warthogs per day. On and on forever. Or not forever. At some point, now we're just going to magically say that there's a constant number of warthogs, 512. And then you can use whatever numbers you want to. But okay, there's a silly function, and it's like a piecewise linear function. This is one piecewise linear model of warthog population. And that's cool because there is no concept of a half of a warthog. So we could try to model this as a smooth function, But there is no such thing as a half of a warthog. And so it's kind of like that first function that I drew was the more realistic thing, and then this other one is an extrapolation, like a smooth model of a few data points. Yeah. I don't know. I think that's an interesting model or application. I mean, that is a function that matches this question statement. Another shape of another curve that might be accurate would be like this. It's way simpler. There are 0 warthogs, then at some point there's 1, and then at some point there's 2, etc. And this one, I think we might be able to actually write down. This is 512. This is like y equals negative 1 over x plus 512. I think. And it's kind of like it's a way simpler model, but I think it's less realistic because in truth, warthogs would be going above and then below, above and below the asymptote that it's describing. Cool. Let me answer a question. Hello, what do you think about Calculus, a Complete Course by Robert Adams? Never heard of it. Never heard of it. Are you taking a course based on that? I'll take a look. My guess is that it's not as wonderful and beautiful as this book, because I am the #1 fan of this book right now. It's just so good. I love this book. Taalman and Cohn. But I'll look into this one. I'll write it down so I don't forget. Calculus, a Complete Course. By Adams. We'll take a look. I'll try to find some reviews and stuff. Are you using it? All right, so 0179 made us use our imaginations for a moment. It was nice. I like it. I wouldn't say that it was a hard problem. So I'm going to give it a nice, easy cross through. All right. Link to book mentioned. Which one, Taalman or the new one that this person mentioned? I don't have it set up yet, but Taalman.themathhobbyist.com will eventually link to it. I don't know why my keyboard's not working. Why isn't my keyboard working? What's going on with my computer today? Alright, I'll do it just for you, because I was going to pull up this link anyways. I'll do it just for you. Taalman? Oh, here's Taalman. I don't know. Adam Eck can find that link, or you could probably Google it and find it. I've never heard of it. I can't recommend it. I'm not going to post a link to a book I can't recommend. Okay, so we've done a lot. What time is it? I have an appointment at 1, so I gotta get going. All right, so we've done a concept problem. We've done an application problem, or we did several skills problems. We did an application problem. Number 89 is now going to be a proof problem. And I think anytime you have a proof, it's going to be a medium difficulty. I haven't looked at it yet, so this is, in a sense, this is a reaction channel. You could call this a reaction channel. I'm reacting to some textbooks in a weird way because I'm a fucking nerd. Welcome to the community. I hope you all are enjoying this and that you are studying and enjoying your own mathematics that you're learning. Yeah, I bought it, but not yet used. Right now I want to focus more on linear algebra. Well, you enjoy my linear algebra videos, perhaps. I did linear algebra last week. Next week I'm going to do number theory, and then I'm going to come back to linear algebra. I love linear algebra. Linear is wonderful. All right, number 89, proofs. Use definition 0.2 to prove that the range of the function f of x equals 3x minus 1 is the real numbers. Okay, I don't think that's that scary. The link I posted was the Adams book. Yeah, unfortunately, I don't think you all can post links because YouTube will block links. But, hey, Mode Danish, how are you? How's it going? We're studying some fairly simple functions today. And just hanging out. Adams Calculus Complete Course. Here's the there's a newer edition. Yeah, I mean, it looks expensive. I'd suggest that you should get Taalman and Cohn. Get Taalman and Cohn. It's such a good book. Hey. Good to meet you. Good to meet you, Mode. All right, use definition 0.2 to prove that the range of the function f of x equals 3x minus 1 is R. Okay, so something I love about Taalman's book so far is that she is very organized everywhere in the book. And the whole book has like a really nice color coding, including like yellow boxes for definitions. Everything's indented really clearly, like really like consistently, like really so organized. I love it. So I'm going to rewrite definitions as we go. Definition 0.2. Domain and range of a function. You know what? I'm going to be lazy on second thought. I don't want to waste y'all's time. I already did this yesterday. Let's copy it right now. The domain and range of a function. It does take a little long to write things out, so let's just copy this. Yoink. Oops. Okay, so there's our definition of the domain and range of a function, okay? If f is a function between subsets of R, then we will take the domain of f to be the largest subset of R for which f is defined. Okay, so okay. This is an interesting thing to prove. I'm going to put this to the side. Oops, that didn't work. It's off the side of the page. Okay, I have it down here so we can reference it if we need to. Domain and range of a function. So the domain is the largest subset of the real numbers for which f is defined. So kind of hard to call this a proof. I don't know how to. All right, so proof. We claim that the domain of f equals R. Let x be any number, any real number, then yeah, whatever. Let's be clear, because like x is usually used to be like the variable, the letter of a variable. Let a be any number in R, then f of a equals 3a minus 1. This number is defined. So a is in the domain of f. I don't know, QED. I think we're done. Like it's an easy proof. Easy proof. But you still need to think of how to logically write down a mathematical argument. Like, we claim that the domain is R. How do we prove that the domain is R, is all real numbers? Let A be any real number. Then we calculate, we see that f admits A, that f, we can plug in, quote unquote, A into the function. This number is defined, so A is in the domain of f, and therefore the domain of f is the real numbers, because we just showed that any real number is in the domain. I think that's a reasonable argument. 89, I'm going to go ahead and call it good. And it wasn't so hard, so I'm going to give it a green check mark. Now 97. What is 97? Fine, sir. And sir, what about you? How am I doing? I'm doing great. I'm doing very good. I'm having fun over here. I just really like math, y'all. I really like math. Even easy, simple math like this. Like, I just love showing it to people, getting questions, talking about it. So if you want me to be your tutor, I can be your tutor. Okay, let's keep going. Finally, we have another problem from Taalman. I'm calling this problem 97, but 0.1.97, this is a thinking forward problem. What does it say? Evaluations for slopes and derivatives. Evaluate each function at the values indicated. Simplify if possible. So this problem, the first one is going to be f of x equals 4 minus x squared. Find part A, f of 1 plus 0.01 minus f of 1 divided by 0.1. Part B, f of 1 plus 0.001 minus f of 1 divided by 0.001. Cool. Okay, so I know where this is going, but thinking forward, this is showing us a cool thing that we will define later on in a future section. So I like this presentation. I think it's neat. So for f of x equals 4 minus x squared. Now we have 4 minus 1 plus 0.01 squared minus f of 1. So this was all f evaluated at 1 plus 0.01. And then this is going to be f evaluated at f of 1 divided by 0.1. Okay. We can see that the 4's are going to cancel out. And then now we have minus 1 plus 0.01 quantity squared minus a negative 1, which is positive 1, all divided by 0.01. And then we'll do one more in this direction. I know that a plus b squared is going to be a squared plus 2ab plus b squared. Okay? And I know 0.01 is 1 over 100. I'm going to use both of those facts here. So here, I know that this is going to be 1 squared is 1. 2 times 1 times 0.01 is going to be 0.02. And then 0.01 squared, well, we could write it as a fraction or as a decimal, but it's going to be 0.0001 plus 1, all divided by 0.01. That positive 1 and negative 1 cancel out. We're going to have negative 0.02 minus 0.0001 divided by 0.01, and then we're going to ask ChatGPT about that. But I see that this is really the only part that matters. This is going to be about negative 2. We could ask ChatGPT for the exact answer of that. But it's going to be a little less than negative 2. Okay, so that's one solution. Let's do another solution in a different color. 4 minus 1 plus 0.001 quantity squared dot dot dot. It's going to be the same thing. It's just that now we're ultimately going to come to negative 0.002 minus 0.00001, I think. Let's ask ChatGPT. 0.001 times 0.001. I got that wrong. 1, 2, 3, 4, 5. Oh no, 1, 2, 3, 4, 5. I got that right. Okay. Divided by 0.001. And again, this is going to be roughly 2. And then we're going to subtract a tiny bit. But now, this tiny bit is going to be even tinier than last time. Last time, it was just a little bit less. Oh, this is minus 2. So it's roughly 2. We could find the exact numbers, but it doesn't really matter. Yeah. Hey, thank you, Mode Donish. I appreciate it. Lots of love to you as well. I'm glad that you're enjoying this, because I think it's fun. I think it's really, really fun. It's fun for me to try to explain math and to try to rebuild it as a hobby. Minus 2 minus epsilon. So this is it's going to be just a little less than negative 2. And we could ask ChatGPT to find out exactly what it is. And then this one is also going to be a little less than negative 2, but it's going to be even closer to negative 2 because this term is going to be smaller because that number is just so much smaller, 0.0001. Okay. I'm going to say that we did it. That's number 97. If it was a homework problem of your own, you would probably you would not get credit for that. You should probably find the exact answer. So I will challenge you to ask ChatGPT on your own on that one. There's 97, and cool. We have just successfully done one problem of each kind from Taalman's first section. That was fun. And now we can bask in the glory of this table of contents and how we are getting somewhere. We've crossed off several problems. So thank you all for watching. This book is terrific. Everything is so neatly organized in review, notes, concepts, skills, applications, proofs. I don't know if we did any review. I don't think, you know what? Let's do problem A. I don't think I did a review problem. I just realized. What is review from the first section? 01A. Yeah, thanks everybody for watching. I'm really happy y'all are enjoying this stuff, because I do very much. All right, so this is called a thinking back problem. Describe each in interval notation. Part A is x not equal to plus or minus 3. Part B is x less than 0 or x greater than 10. Part C is x greater than negative 2 and x not equal to 5. And then part D is x not less than 3 and x not equal to 4. I like that last example. That's neat. I like it. All right, so x is not equal to plus or minus 3 in interval notation is going to be negative infinity to negative 3 union 3 to infinity. X less than 0 or x greater than 10. Less than 0 is going to be negative infinity to 0, or is like the union. It's like all of these numbers and all of these numbers. Like x is in this one or in this one of the two sets. X greater than negative 2 and x not equal to 5. Greater than negative 2 and x not equal to 5. Yeah. X is not less than 3. We could rewrite that as x is greater than or equal to 3. And x is not equal to 4. So, if x is greater than or equal to 3, then x is, we have bracket, square bracket 3 to 4, and then 4 to infinity. Those are all parts A through D. And here I was lazy and I used a dot dot dot. So let's try to smash these in. A, B, C, D, E, dot dot dot. And we just completed 1, 2, 3, 4 thinking back problems. All right. Thank you all for watching. This is fun. Next time we're going to look at some harder stuff. I'm going to write down probably the definition of the limit according to a few different books. So, hope you're enjoying it. Lots of love from America. Thanks for watching. My name is the Math Hobbyist. Peace. Have a wonderful day.